This is the narrowband low noise amplifier, which you can find in 2 previous videos of this series. The schematic diagram is right now like this, and what I will do is to insert a resistor here between the drain of the FET and the decoupling capacitor, and then couple the drain to the low impedance point at the emitters of the bipolars. This will bring the drain to have the same AC voltage as the emitter, and that will remove the Miller capacitance here, I think, and I think this will improve gain of the JFET amplifier. The original performance is like this. Gain 10 dB and the Q is 70,000. So I have put 47 ohms here between the drains and the decoupling capacitor, and then a capacitor from the emitters of the bipolars to the drains of the FETs. As a result, the frequency has changed because I have eliminated the drain to gate capacitance this way. The gate and the drain are now moving with the same AC voltage. The Q has improved dramatically to 126,000, and the gain is 5 dB higher. And the frequency has shifted because the capacitance from the gate to the drain, which was previously grounded, is now eliminated by this trick. So I have to retune the tuning capacitor. I am now looking at the output of this unit when it's running as an oscillator. Here is the noise level with a 50 ohm dummy load connected to the measurement system. And here is the oscillator. It is 2.05 dB. And that is at the power level of 19 dBm. The directional coupler is a minus 20 dB unit. I now remove feedback. That causes the noise floor to go down by 0.35 dB. That's much more than before, something that I cannot explain. Changing the schematic diagram like this, with a capacitor from the drain of the JFETs to the source of the emitter follower, that has changed what I measure, like you can see here, from 1.6 dB to 2.05. That makes the noise about 1 dB stronger. Now, the sideband, now since the power is also 1 dB stronger, the sideband noise in dBc per hertz is the same. What happens when I remove the feedback is now much bigger, so I can get this result. But this is a bit of guesswork. I don't know so much about this. What would be desirable is to get the tools to measure close range phase noise. The modification has improved Q by a factor 1.8. The noise in the close range should have gone down now by 1.8 squared. That is 3.2 times, that's about 5 dB. Whether this is true or not, I don't know. I cannot measure close range yet. The wide range performance minus 190 dBc per hertz phase noise is determined by the output transistors, the power transistors BF458. These are the best ones I have found in my junk box at the moment. I have tried various RF transistors and they are not anywhere near as good as this one, but there are probably modern transistors that can do better. I don't know, I've tried to search the internet, but I cannot find information about what is good for this purpose. Means noise current, equivalent noise current at 10 megahertz for power transistors.